Hello class. So in this lesson I'm going to tell you, we're going to continue with the binomial theorem, and we were doing this one was the next example to go through. This example number 2, find the given term in the expansions of the following binomials. This is the binomial raised to the 7th power, and I'm asking you to find only the 5th term. We don't really need to expand the whole binomial to the 7, right? Like we don't really need to get all the 8 terms, because I'm basically just asking you for this term, the 5th term in such expansion. Like we said before, there is a formula that we discovered in class, right? So that we can get any specific kth term. And what does this mean? It means basically the term which is at the position k in the expansion, right? That's what it means. And that kth term will be given by n choose k minus 1 a to the n minus k minus 1 times b to the k minus 1. I know it may look like a difficult formula to learn, but you can actually deduce it from watching the binomial theorem. By paying attention to the binomial theorem, you can actually deduce this formula like we did in class. So let's apply it in here, right? If I'm being asked to find the 5th term, then basically k will be equal to 5. And all I need to do is, if I want to find this term, the 5th term, I need to replace k equals 5 in this expression, and obviously my n would be 7. So n equals 7, k equals 5, and therefore the 5th term is going to be equal to 7 choose 5 minus 1. There you go. And then the first number in the binomial raised to this exponent, my first number is 3x squared. So let's write it down, 3x squared raised to the 7 minus 5 minus 1 times the second number in the binomial, which would be this 5y to the 5th raised to the k minus 1. There you go. So as you can see, I'm basically following this formula to the extreme. Every single thing I'm replacing, and that's it. Then it's just a matter of basically simplifying all of these. You have 7 choose 4 in the end, and then you have 3x squared, 7 minus 4, which is 3, and then 5y to the 5th to the 4. There you go. Okay, and then finding 7 choose 4 and elevating this number to the cube and elevating this number to the 4. But I'm gonna keep it in this way. You can do the rest in the calculator. So that there you go. And something very similar for this one. You have this binomial to the 12. You need to find the 7th term. Okay, so remember, we first have to put this binomial into a binomial in the form of an addition, like so. There you go. To the 12, right? And therefore, now you can go on finding the 7th term. So in this case, what is your n? Your n is the exponent, which is 12. What is your k? That's the number of term that you're looking for, 7. And then once again, just attend to the formula, which is this. There you go. Okay, so basically we have to perform 12 choose k minus 1. That's going to be 6, right? 12 choose 6. And then the first number raised to this exponent. The first number is this. 2w to the 4 raised to the 12 minus 6 times this number, the second number in the binomial, raised to the k minus 1, which is 6. Okay, and then you can pick it up from here, right? This is going to be, in the end, it's going to be 6. And then calculate this number using the calculator or the formula and elevate each of these numbers to the respective power, and you're done. Okay, so that's how you find the whatever number of term that you're given using this formula, without expanding the whole binomial, right? Because it would be pointless to get all the terms if you only need one of them. Okay. Now, I'm going to tell you about something called the Pascal's Triangle, the role of Pascal's Triangle in the expansion of a binomial. So first, let me tell you what the Pascal Triangle is. Pascal's Triangle is a geometrical arrangement of numbers that can give you the binomial coefficients right away. Such triangle is the following. First, let me remind you what binomial coefficients are. The binomial coefficients, guys, are all of these factors that appear at the very beginning of each terms. Of each of the terms in the expansion, these numbers are known as the binomial coefficients. All of these combinatorial numbers, n choose 0, n choose 1, n choose 2, etc., these are known as binomial coefficients. And you can get this by either the formula that I gave you, so you can compute these things manually, or you can get them through the calculator. But there's also a very fast way to get these ones, and that way is by using the Pascal triangle. So let's go there. So this is the Pascal's triangle. It's an arrangement that looks like a triangle, obviously. These sides, as you can see, are composed of ones. Each of these is understood as a row. For example, this is the first row, second row, third row, fourth row, fifth row, and so on. And there's a way to build each of the rows in the Pascal triangle. The first thing you do is this. You begin with the row 1. You begin with 1. So that's a definition. The row 1 will be just 1. The row 2 will be 1 and 1 in this configuration below the one at the top. So all of these three numbers, guys, these are definitions. Like, you have to start with this. That's the beginning of the construction of the Pascal's triangle. And then each of the consecutive rows, each of the next rows, the third row, the fourth row, the fifth row, and so on, you can build them. How do you build them? Okay, the first number and the last number will always be 1. Always, as you can see. Okay, so the numbers at the extremes are 1. And each of the numbers in the middle of the Pascal's triangle can be obtained as the addition of the two numbers on top of it. So for example, this number, which is 2, can be understood as 1 plus 1. As you can see, 1 plus 1 gives you 2. This number, which is the 3, can be understood as 1 plus 2. 2 plus 1, 3. 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4, etc. 1 plus 4, 5. 4 plus 6, 10, and so on. You see? So each of these numbers, I'm going to highlight this number. This number is the addition of the two numbers on top of it, like that. And that's how you build the Pascal's triangle. Once again, you begin 1, 1, 1. That's how you start. And then 1, this plus this, 2, and then another 1. 1, this plus this, 3, this plus this, 3, and another 1. 1, this plus this, 4, this plus this, 6, 4, 1, etc., etc., following the same pattern. Okay, so that's how you construct this geometrical arrangement known as the Pascal's triangle. What is it for? What is it for, guys? Well, all of these numbers that appear in the rows, once again, let me label the rows. First row, second row, third row, fourth row, fifth row, and so on. These guys, these numbers, are the binomial coefficients. The binomial coefficients when you expand a binomial using the binomial theorem. What do I mean by that? I mean the following. So for example, let's suppose that I give you a very simple binomial, 2x squared plus 3y to the 4. and you want to raise it to the 4. Okay, according to the binomial theorem, the expansion will start with this. 4 choose 0, then this number to the 4, then the second number to the 0, that's the first term, plus 4 choose 1, the first number in the binomial, to the 3 now, 2x squared to the 3, 3y to the 4, to the 1, and so on, right? Then 4 choose 2. Let me complete the whole thing quietly. Just pay attention to whether what I'm doing is right or wrong. There you go. So this is the full expansion, guys. This is the first term, second term, third, fourth, and fifth term. We have 5 terms in the expansion of this binomial to the 4. Very good. Now, once again, what are the binomial coefficients in these terms? The binomial coefficients are this number, 4 choose 0, that's the first binomial coefficient. 4 choose 1, that's the second binomial coefficient. 4 choose 2, 4 choose 3, 4 choose 4. So we have 5 of them. And they can be obtained, once again, through the formula that I gave you, through the calculator automatically, or by using the Pascal's triangle. If you go to the 4th row, which is the corresponding one for an exponent of 4, okay, if this is your exponent and if your exponent is 4, you go to the 4th row, and then you can see that I mean, as a matter of fact, I'm 1, 2, 3, 4, 5. No, it's you got to go with this one, guys. Sorry, for the 5th row, you have to go one more. You have to go one more. Okay, like you start counting in here. 1, 2, 3, 4. There you go. If we start counting, we don't count the number 1 as a row. Okay, this is like just like the beginning of the Pascal's triangle, and we start counting from here. This is row number 1, row number 2, row number 3, row number 4. There you go. And these numbers 1, 4, 6, 4, and 1, these will be the binomial coefficients. If you calculate 4 choose 0 in the calculator, you will get 1. If you calculate 4 choose 1 in the calculator, you will get 4. 4 choose 2, that's 6. 4 choose 3, that's 4. And 4 choose 4 is 1. So as you can see, you can get these numbers, which may be complicated if you don't have a calculator, very easily through the use of Pascal's triangle. And the same goes for any other binomial raised to any other exponent. Let's suppose that I give you this one, 3x plus, let's say, 2y to the 6, okay? And if you want to know the binomial coefficients that you will get, which are 6 choose 0, right? And then 6 choose 1, 6 choose 2, all the way until 6 choose 6. So you have 7 of them. You have to go to the 6th row, which is 1, 2, 3, 4, 5, 6. You have to construct all these rows. And this row comprised of these numbers 1, 6, 15, 20, 15, 6, and 1. Those are going to be the binomial coefficients that will appear in here. So 6 choose 0, that's going to be 1. 6 choose 1, that's going to be 6. 6 choose 2, that's going to be 15, and so on. Now notice another very important fact, guys. This triangle is symmetrical. It's completely symmetrical. Let me raise this thing for a moment. The triangle is symmetrical, right? Look, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. If you drew a line in the middle, you can see that the symmetry is perfect. So if you get the first half of the Pascal's triangle, like if you already got these numbers here, 1, 5, and 10, then you know that the remaining terms should be 10, 5, and 1 in that order. It's this line acts kind of like a mirror, right? This is the mirror reflection of these ones. 1, 6, 15, 20. You have arrived at the middle, right, of the triangle of this row, and therefore the next terms should be 15, 6, and 1, and so on. So you don't need to really get once you have obtained half of the row in this triangle, you can write the other half just by this principle of reflection, right? Just taking into account that this figure is symmetrical. Okay, so now let's put this thing to use with this example. Use Pascal's triangle and the binomial theorem to expand this binomial to the 4. Okay, so here we go. We have 2x to the cube plus 3y to the second power raised to the 4. There you go. So how many terms are going to be in the expansion? We know that there will be 5. We know that already. There will be 5 terms. Okay, and according to the binomial theorem, this is going to be equal to 4 to 0. Let me do this very quickly. 2x to the cube to the 4. Okay, just pay attention to it. This is according to the binomial theorem. So I'm just writing down the formula of the binomial theorem. There you go. There you go. It's 5 terms. And now with the use of the Pascal's triangle, I can get this number, this number, this number, this number, and this number without the calculator and without the formula for combinations. So let's construct Pascal's triangle. We start 1, 1, 1, 1, 2, 1, 1, 3. This plus this is 3. This plus this is 3. 1. And then 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then 1. Okay, and this is the row that we need because my exponent is 4, and this is the 4th row. Remember that we start counting the rows in here. First row, second row, third row, 4th row. So there you go. And therefore, I can just substitute this by these respective numbers, 1, 4, 6, 4, and 1. So it's going to be 1, 2x to the cube, to the 4, 3y to the square, to the 0, plus 4 choose 1, which is going to be 4. There you go. 2x to the 3, to the 3, 3y to the square, to the 1, plus 4 choose 2, which is this one, 6. We have already covered this 3. And so you just keep doing this, guys, right? So I hope you have understood how to use this triangle in order to get, once again, what is the name of these things? Binomial coefficients. All of these things, which is a number that comes from combinations, that is known as a binomial coefficient when they are written in the context of the expansion of a binomial, right? So you can continue doing the rest. And now the only thing that remains to be done is elevating this to the 4, this to the 3, etc., right? And simplify as much as possible. Okay, so there you go. That's the use of Pascal's triangle. And now I'm going to put you to use to solve some problems from the book, the exercises that come next. And that's it, guys. Thank you.